Hi, I'm Andy Novick. In this video we're going to talk about T-SQL functions, what's the problem with them, and a solution to it. If you want to read this material, it's available on my website at this address down here, or you can use this bit.ly address here. If you want to send me an email, ask a question about this, here's my email address. You can always visit the website. Let's talk about the types of functions. There are three types of functions. Scalar functions return a single scalar value. You're familiar with this from other programming languages, I'm sure, and they're quite similar. Table-valued functions return a table of values that are used in the from clause, and the table is defined with an @table variable. Inside them you can do a lot of things that you might be doing in a stored procedure and creating just one result set. Inline functions are like table-valued functions in that they return a single result set, but they do so by defining a single select statement that is treated by SQL Server as a view. Well, that's a quick review. If you'd like to read more, I wrote a book about T-SQL functions 10 years ago. The book is still mostly valid except for things like talking about the query analyzer. You can get a free PDF of it, and it might serve as a nice intro if that would help. And you can get that online at that address, which is also this bit.ly address. So let's look at a function, and for our example, we're going to use the exponentially weighted moving average. Well, here's the formula. You may recall this from high school if you think back real hard. It's actually quite simple. It takes two values, the value today of something, and the value of the moving average yesterday, and then a smoothing factor and a number of days. The smoothing factor is usually like 2, and it helps smooth things out. The number of days lets you specify how long a time frame you want the data to be included for. Sometimes you'll see these numbers combined into a single factor, and that's often like 0.18. But we're going to express it like this with both of those. Don't worry too much about the math. It's just arithmetic. It looks pretty simple when you get it to T-SQL. So let's take a look at it when we get it in T-SQL. So we have our create function, returns a float, and then all we have to do is return a single case statement to do the formula. We have to deal with null values, in which case we just return the value today, or we implement the formula and then end. Scalar functions have a begin and end, and you'll see inline are a little bit different. So what's the problem with scalar UDFs? Well, the problem is row by row processing. SQL Server has to stop at every row and execute the scalar UDFs that are on that row and then continue. Sometimes this is referred to as row by agonizing row, or R-bar. You may have heard this term in reference to cursors. The second problem is that use of a scalar or table-valued function inhibits parallelism in the query. Now, I don't know about what you're running on. I don't know a lot of people who are running on single processor systems anymore. Making use of the available cores in your system has got to be an important part of scaling your application up. Here's a query plan with a scalar, and we'll see later what the difference is when we get a parallel plan. There isn't much choice about what to do. It has to do an index scan to get all the data from security returns, and it has to do a table scan to get all the data from today's returns. Let's flip over to Management Studio and take a look at what the function does. Here's the function again, same one as in the PowerPoint, and I've already created it in this database, and we're going to use it here. Alright, so right here is where we're using the function. We're taking values from our security returns. That was basically yesterday's values, and then we have our today's returns table, and we're going to combine them with the exponential moving average scalar using 21 days and a default smoothing value. So let's select the query and execute it. And there's our parse time. We returned 121,317 rows. Okay, here's our CPU time, 421 milliseconds, and our elapsed time, about the same, at 427 milliseconds. Well, that may be fine, and if those numbers don't bother you in your application, then no problem. But if you have maybe a lot more rows, maybe 100 million rows, or even a million rows, or if that number is a problem, you may want to do something about it. Well, let's take a look at what's happening, and we'll use Profiler for that. I'm going to start a new trace, and I'm going to start with the blank trace and just one event. In stored procedures, stored procedure completed. User-defined functions, at least scalar and table valued functions, are treated by trace as stored procedures. So we'll run that. Let's maximize it, turn on off auto scroll, and go back to run our query again. Oops, that didn't run it. Now we've got to get rid of that temp table. I use the temp table because the rows don't have to be returned to the screen, which sometimes messes up the timing. So let's execute it again. Now it's taken a long time. Let's flip back to Profiler and see what's happening. And oh, a lot of rows here. If you look down here at the counter, 80,000, 90,000, there's going to be a row in trace for every execution of the function, and that's once per row that is called on. No wonder there's so many events, and it takes so long. Now let's pause that and move back to the example. We can see it probably took 14 seconds, but that's because the profiler is slowing it down because there's so many events. So I grabbed the query plan and enlarged it so it's easier to see. And there isn't much choice about what to do. The security returns table has to be read in its entirety, so it uses the index. And today's returns also has to be read in its entirety. It's got no index, so it's just a table scan. And they're joined up, in this case, by a hash match. Not much else choice there. Notice, I'll point out how you can tell in a minute, this is not a parallel plan. So what's the solution? The solution is using an inline UDF, rewriting the scalar UDF as an inline UDF. Essentially, this is a view with parameters. And what happens is the T-SQL optimizer merges the UDF's select statement with the rest of the query, producing a combined query. This works in SQL 2000 all the way through SQL 2014, and I'm sure beyond, although there may be other solutions someday. Here's our exponential moving average function as an inline function. Very similar to the scalar function, same parameters, but this one returns a table, and then it says as return, and a single select statement. The case statement is really identical to the scalar function's case statement. In fact, I've lined them up, and I can sort of flip back and forth. Let's give that a try. So here's the scalar, here's the inline, scalar, inline, scalar, inline. Notice also this inline function doesn't actually access any data. Now it could, but it doesn't. It doesn't have to. All it has to do is return an expression. Usually it returns an expression based on the parameters, and in some other cases you'll find that inline functions will be reading data and combining data as well. So let's flip back to Management Studio, and we're going to go and recreate the inline function, and we're going to get rid of our example table and just look at how you use the inline function. Unfortunately, inline functions are not drop-in replacements for scalar functions. When you use an inline function, it goes in the from clause, and you have to have a subquery in order to replace the scalar function. The parameters are the same, but we now have this select statement, and the column is named the same. The rest of the query is identical. Now, SQL Server is not going to just execute this inline function for every row. Instead, it's going to take the definition you've provided and combine it with the rest of the SQL and produce its plan. So let's give that a try. And execute it. And now that was fast. Let's see. So our CPU time is 250 milliseconds. Not quite half, a little bit more than half than the scalar function, but the elapsed time, that's only 64 milliseconds. So roughly, I think an eighth of what it was in the scalar function. That's fabulous. Let's flip over and take a look at the query plan. I grabbed the query plan off the screen to enlarge it, and I blew up this one little node there. Notice this orange circle with two arrows pointing to the left. That tells us that this is a parallel step, meaning it will use multiple cores to implement this step. And you can see those orange circles throughout the plan, except to the very end when it returns the results. Using all our cores is what makes it much faster. And if you go back to Profiler, well, there really isn't anything else there. Is it okay to use a UDF? Well, if you're using something like this, where you have a single function execution, it's great. Functions are a way to consolidate and represent business logic in a reusable form. So this is great. Do it any day. Now, what about a more complex query where you're using it on every row of a select? Well, maybe this is okay if the number is small. If there's a small number of rows involved, it is okay. Or if the scalar UDF is converted to an inline UDF, you don't have the overhead of this scalar, and you can get a parallel plan, and it works great. I'm Andy Novick. I hope you enjoyed this video of T-SQL functions, problem and solution. You can read this article and all the material and download the sample file and a PDF of the slides at this address.